So hello and welcome back. Today let's examine a landmark-based sensor model example. So assume we have a robot located in the environment at a location or pose of 0, 0, 0 degrees with a known landmark in the map M at 3 meters, 4 meters, or at a distance of 5 meters with an angle of 53 degrees from the robot. Assume the robot sensor has a measurement of 5.1 meters and 60 degrees for the distance and bearing with a distance noise error of 0.5 and a bearing noise error of 0.5. Find the probability of the robot's measurement Z, where we have that the probability of Z given X and M, which is the pose and the map, can also be thought of as the probability of Z given the expected measurement to the landmark, Z expected, or the probability of that distance and alpha measurement to the landmark given X and M. And using the Markov independence assumption, we can write that as the probability of that distance given the robot's pose and the map times the probability of that bearing given the robot's pose and the map. So the algorithm for the landmark detection probabilistic model is given a measurement with a landmark ID with an angle alpha and a distance d to the robot pose. So we're going to input z, which is equal to I, d, and alpha. And in our case, I is just a 0 because we only have one landmark in the environment. And x is equal to x, y, theta. So that's 0, 0, 0, or the pose of the robot. And the expected distance is going to be given by the Euclidean distance, mx of I minus x squared plus my of I minus y squared, where mx of I and my of I represent the landmark's known position on the map. And alpha hat, which is our expected angle of 2, arctan 2, of my of I minus y, mx of I minus x minus theta, which is the angle or bearing of the landmark with respect to the robot pose. Now to calculate that probability using our independence assumption, then we take the expected value for the distance minus the sensor distance as the mean for the normal or Gaussian distribution, where epsilon, which is our error, ends up being our standard deviation, times the probability of the expected bearing minus the bearing from our sensor measurement as our norm for our Gaussian distribution. And then we have the error for our angle, where error for the angle and distance was given as 0.5. And then we return the probability of that landmark detection. So please recall that our normal distribution or probabilistic motion model is given by the following, assuming a zero mean for the Gaussian distribution. And we use the formula 1 over the square root of 2 pi b squared, where that is our standard deviation b, e to the negative 1/2 a squared, where a is our mean, divided by b squared. We write this as a function in Matlab. So first, our function is here at the end of our script, where we have the function p is equal to probability of the normal distribution, where as is the mean, bs is the standard deviation, and we didn't stick in the formula that we just saw, where it's 1 over the square root of 2 pi bs squared times e to the negative 1/2 as squared over bs squared. So now let's go back up to the top of our code. So this first block here is our problem statement. So this is where we put in the robot pose, x, y, theta. We put in the landmark, mx of I, my of I. We put in the robot sensor data, which is 5.1 meters, 60 degrees. And we put in our errors, which was 0.5 for our bearing and our distance. And then we run that section. And over here, we print out the robot pose, the landmark position, as well as the sensor data, 5.1, 1.0472. Then our distance and bearing parameters, which is d hat and alpha hat, we run that section. And we see that d hat is 5 and alpha hat is 0.9273. And these are going to be compared to the ground truth for the landmark up here, 5.1, 1.0472, which is the sensor data. And then for the probability down here, we calculate d hat minus d and a hat minus a. And then we have d error and a error as our standard deviation. And then we send it through our normal distribution. So when we run that section, we see that the probability for the distance is 0.7821. The probability for the bearing is 0.7753. And then when we multiply them together, the probability of getting that sensor measurement Knowing the robot's pose as well as its location in the world for the landmark is 0.6. And this concludes our landmark detection sensor model. I hope you've enjoyed. Please come back again and make it a robotastic day.